Okay, so like I said, somebody asked about this question. I'm not sure what was the question about it. So whoever it was that asked this question, this is spring 16, numbers 1 and 2. But nonetheless, I want to work through it anyway because it is a good question. And then if y'all have questions that are specific, I'll address those. But there are going to be several circuits. Probably half the quiz, I mean more than half the quiz actually will be circuits. So make sure that you can do series, parallel, and combination circuits. Probably 5, 6, 7 questions either are just going to be circuits. So the first one is like we were doing in class today. What is the equivalent capacitance of this circuit? So the first thing you want to do is look for the part that is either series or parallel. So which capacitors do you think that we'll start with in this circuit? We'll start with the 3 and the 6 because those are purely in series. So I'll start with these two. And by now you should be getting familiar with some of these numbers, right? Because a 3 and a 6 in series is equivalent to what? 2. Right, 1 over 3 plus 1 over 6, that's equal to 2. So I'm going to replace that with a 2 microfarad capacitor. And when I do that, I'm just going to redraw it. It all comes back together. I get a 3 microfarad there. And I'm just going to write the numbers. I'm not going to put the units. So I have 3, 2, 1, and 3. And then I combine that 2, 1, and 3. Oh, but look, that's just 6 microfarads. So I get a pretty simple circuit. Even though it looked complicated in the beginning, I find that this is a circuit with a 3 microfarad in series with a 6 microfarad. And then I can finally combine that down to say that this is a 3 and 6 in series is 2 microfarads. So that's the answer for this one. D is the equivalent for that is 2 microfarads. But then a harder question is to ask, what is the voltage? Now really to answer number 2, what is the voltage across the 1 microfarad capacitor, you really need to know all the voltages. Like we did in class today, let's think through what these voltages are. I'll do the volts in black here. So I get 12 volts across the 2 microfarad capacitor. And, you know, I know then that I have 24 microcoulombs on that capacitor because Q is equal to C times V. And so if I get 24 on that one, I get 24 microcoulombs there and 24 microcoulombs there. That means that I have 24 divided by 3, that's 8 volts on that one, and 24 divided by 6, that's 4 volts on that one. Remember those little rules I told you, that the small capacitor carries a big voltage, the big capacitor carries a small voltage. And we see that here. The small one has 8 volts, the big one has 4 volts, and they're different by a factor of 2, just like the 3 and the 6 microfarad capacitors are different by a factor of 2. So now carrying that on, stepping back, I just copy the 8 volts to that capacitor because that's the same one. And then this 4 volts on the 6 microfarad capacitor, because the capacitors that make up that equivalent 6 microfarad capacitor, this one right here, because they're in parallel, capacitors in parallel have the same voltage. So I get 4 volts here, 4 volts here, and 4 volts here. Okay? Now, that's the answer, right? Because I wanted the voltage across the 1 microfarad capacitor, so that's 4 volts is the answer. Because that was the voltage right here. Well, let's take it a step forward and say, what is the voltage across the 3 and the 6 microfarad? Because it's a little more difficult to do it the way that we were doing, because it's just, they're going to be not even numbers, not integers for those, because I can't think of an integer, 2 integers that add up to 4, well, one is twice the other in order to give me that 4 volts. So the way that I'm going to do this is I'll say the charge on this capacitor is 8 microcoulombs, right? 2 microfarads times 4 volts is 8 microcoulombs. That means that I have 8 microcoulombs here and 8 microcoulombs here. And then if I want to find the voltage is going to be Q divided by C. So that's 8 divided by 3, 8 thirds volts. and 8/6 are 4/3 volts. So those are the voltages across those. Notice the small capacitor has a big voltage, the big capacitor has a small, or the big capacitor has a small voltage, yes. And also they add up. 8/3 plus 4/3 is 12/3. 12 divided by 3, that's equal to 4. So everything checks out. And when you do these combination circuits especially, and the series and parallel, make sure that you go back and just check that all your voltages add up to equal to the total voltage, that your charges are all consistent. There are several checks that you can do just to make sure that you got the answers right. Okay, Elena? Yeah, so to get the voltage right here, I was looking at these two capacitors, the 3 and the 6, and so to get the 8/3, I said 8 microcoulombs, that was this charge, divided by 3 microfarads. That was this capacitance.
Oh, because they're series, so they have the same charge?
That's right, they're in series, so they have the same charge. That means that they have the same charge as this capacitor, which is the equivalent. You want me to write down those rules again for you? Or y'all got them? You think you got them? All right, I'll write them down. They're always good to just sort of see. So for caps in series and caps in parallel. First, have the same charge. And I'm going to put in parentheses, and same as the equivalent capacitance. So they have the same charge as the equivalent capacitance. Not two. Caps in parallel have the same voltage. And same as the equivalent capacitance. Whichever capacitance is the equivalent of whatever ones are in parallel, it will have the same voltage as those. 2 is the second rule has to do with the equivalent. This is C equivalent equals 1 over C1 plus 1 over C2 plus dot, 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 dot. And then this rule is C equivalent equals C1 plus C2 plus dot, dot, dot. Now, some of you are doing resistors in series and parallel this week, I think, in the lab. Be careful because these two equations flip-flop. That this is for resistors in series, not parallel, and that equation is for resistors in parallel. So just be careful. The resistor rules are very, very similar, but these two sort of flip-flop. So be careful if you're having that lab before you come to the quiz. I think that's the lab we're doing this week. Third, so I just do this Q equals CV, Q equals CV. And then also that the voltage is equal to the sum of the individual voltages. Plus, So that's like if I have two voltages here, say 8 volts, 4 volts, that whatever they're hooked up to, in this case that would be 12 volts. They have to add up to one another. And like I said, there is a fourth rule over here, but we never use it, and it is that the Q on the equivalent capacitance is equal to the sum of the individual Q values. But not really useful. I don't know if you would ever really use that, but you can see how the rules are all fall in parallel to one another, that they're all really similar in the way that they function, even if they're different in the details. Okay, somebody asked, let's see, I did those, and again, I don't know, somebody had asked about this question, so if I didn't answer your question, please just, ask me. Y'all have specific questions from y'all.
I think it just needed to do the voltage and the charge.
Yeah, let's do that. Remember, 2017 to 2021. That's why I'm pulling your quiz questions. I'm not going to do that every time, but on this one, I want a good showing on this quiz. I want y'all to do well. So that's not a big bank of questions. It's really not. So just spend time reviewing those questions. If you just memorize them, I'm okay with that. That's fine. Just memorize them and do well on this quiz. It will help you when you move into the exam, that you'll understand it better for the exam with the time that you spend on it. Let's find another combination circuit. Um, Number 6. Let's do this one. Consider this circuit. All 3 capacitors are identical. What is the voltage across C1? This one's difficult because there are no numbers in it. So students often mess this up just because you're used to dealing with numbers, but now you don't have numbers. So students sort of freak out a little bit. But it's not any different. Not different at all. Let's just find the equivalent capacitance. I don't like the red. I'm going to have my first equivalent capacitance. I'm going to call it 3C. C2 plus C3 plus C4, that's just equal to 3C, right? They're all the same, so I can just say 3 times that. And then my other one is C. And then I have 12 volts right here. So here I'm sort of forced to do that thing that we did in class, asking, well, what are the voltages on these where they have to add up to equal to 12 and one is 3 times that of the other? Well, there's one way I could do it. I could say that the voltage on this one has to be 3V and this one has to be V, right? Because the small capacitor is going to have 3 times the voltage of the big capacitor. And so I could say 3V plus V is equal to 12, and then solve for V. So V would equal to 12 divided by 4, or 3. That means that this voltage is 9 volts, and this voltage is 3 volts. Y'all see what I did there, the algebra? And I know it's a little confusing because this I'm treating as a variable right here. I'm treating these as variables, not as units, and the variables translate down here. I'm just trying to figure out what is the quantity V, but then up here I use V as a unit. Okay, so that means that the small capacitor has 9 volts, the big capacitor has 3 volts, which is 1/3 of the big voltage, and they add up to equal to 12. We did a couple like that in class today, except usually that was like an 8 and 4 type of separation. Okay? Nice, easy round numbers, okay? It's rare for me to give decimal numbers. Well, like here's one with a decimal number. What is the equivalent capacitance of this configuration of capacitors? I'm not going to do it, but first I would do this. This is 12.5. And then you say 1 over 0.3 plus 1 over 12.5. And then that would give you the answer. I will point out that when you have capacitors in parallel, the equivalent capacitance is always smaller than the smallest capacitor. When you have capacitors in parallel, the equivalent capacitance is always smaller than the smallest capacitor. So I know then that the answer can't be that or that. It's not terribly important for this in this exam, but next chapter it will be more important. We'll see that, how it comes into play for resistors. All right. Y'all holler if you see something that you want to do. I'm thinking number 4 and 5 right here. This is 2017, number 4 and 5. Okay with that? Let's try it where we just, I don't know, sort of, actually, let's see. Yeah, let's just look at this and see if we can figure it out without actually writing anything down. Although, as I said in class, not a good idea. Like, you want to write stuff on your paper because you won't make as many mistakes. But I have 3 capacitors, 3, 3, and 3. What is that equivalent of? 1 over 1/3 plus 1/3 plus 1/3? Right, so this is an equivalent of 1 microfarad. And then I have 1 and 2. That's 3 microfarads. And then a 3 and a 6. That's what? 2. Right, so the answer is going to be 2 microfarads. Now, that wasn't that hard. Like, you should be able to do that, I think, once you get with some practice in your head. But the next part, you really probably want to write down things, because I want to know what is the voltage across the 6 microfarad. So I'm going to go back and let's write down some of these things. I have a 1 and a 2 and a 6. This is 1, 2, 6. Then I combine those to a 3 and a 6, which we've done. So this is 1 plus 2 is 3. That's 6 microfarads. And then this is 12 volts. As we've done on this, the voltage now on each of these is going to be 4 volts and 8 volts. Remember how we're doing this, that I have an additional simpler circuit of 2 microcoulombs, or excuse me, 2 microfarads over 12 volts. So it has a charge of 24 microcoulombs. That means that this has 24 microcoulombs, and this also has 24 microcoulombs. 24 divided by 8 is equal to 3. 24 divided by 6 is equal to 4. Anytime I get two quantities, I can always calculate the third by this Q equals C times V. So I can write these voltages down up here, bring them back. This is 4 volts. If I have 8 volts here, because capacitors in parallel always have the same voltage, I also get 8 volts there and there. And by the way, I'm not asking this question, but if I wanted to know the voltage on any one of these capacitors, do you know what it would be? 8 over 3. They're going to split them evenly. So I'll have 8/3 volts, 8/3 volts, and 8/3 volts. Giving me a total, all of those add up to equal to 8 volts. 8 volts here, 4 volts here, and then 12 volts here. Okay? Make sure that you're not forgetting these things. So there will be some other problems like this, where it's just, hey, oh gosh, this is a conceptual question. So if the area of the plates is doubled, I have a parallel plate capacitor and it's connected to a battery. Oh, so not a simple problem. Let's look at this, okay? So I have a capacitor that's connected to a battery. There's a key word here that the capacitor is connected to a battery. What that means is, as I change the capacitance of the capacitor, that also changes the charge that it stores. So you can think of the battery as like a source of charge. It will always fill up that bowl. No matter how big the bowl gets, it will fill up the bowl to the amount that it can, as much energy as it has. But if I take the battery away, the bowl only has so much charge in it. That amount of charge is never going to change. And then if I change the dimensions of the bowl, or the capacitor, then that will change the voltage. So let's work this one right now. Because it's connected to the battery, that means that the voltage is constant. And that Q will change. All right, so Q will change. So I have connected to a battery with a certain voltage. It has 10 coulombs of charge. And then the area of the plates is doubled. So two equations that are important, Q equals CV, and C equals epsilon naught A over D. So what I'm doing is I'm doubling the area of the plates. That means the capacitance doubles. Now we look at this equation. Because V is constant, if C changes, that means if this goes up by a factor of 2, what's going to happen to Q? Will it go up or down? Will Q increase or decrease? It's going to go up, and it's going to go up by a factor of 2. So the important word here is that this capacitor is connected to a battery. And when it's connected to a battery, it will always have the voltage of that battery. Okay? So the answer then is if the charge doubles, it was 10 coulombs, now it's going to be 20 coulombs. Let's look at another one that's similar but different from that. So you'll see what the difference is in those questions. Give me just a second. See, here's one that's connected to a battery. Here we go. So number 3, this is spring 19, number 3. Here I have a parallel plate capacitor that initially has a potential difference of 10 volts, and then it's disconnected from the charging battery. When I say that it's disconnected from the charging battery, that means that now Q is constant. I filled up that bowl with as many charges as I can, and then I take away the battery. That means that the amount of charge that's on the capacitor stays the same. However, if I change the dimensions of the capacitor, in this case I'm doubling the area of the plate, so I double the area of the plates. That means I double the capacitance. Up here, if I double the capacitance, notice Q now is remaining constant. So if Q remains constant, what happens to V? What has to happen to V if Q remains constant? It goes down, and it goes down by a factor of a half. So whereas it was initially 10 volts, now it's going to be 5 volts. Be prepared for that. I mean, they happen a lot on exams, so you'll probably see it on the quiz of some variation. Oh, let's look at number 5. So number 5 is difficult just because it looks different, but it's really not any different than what we've done already. Number 5, first of all, I'm looking for the equivalent capacitance between these 2 points. So if it helps you, you can imagine that there is a battery like that. In fact, that might not help you very much, but now I can redraw this circuit so that it looks like this. I'm going to rotate it around. I'm going to redraw it so that it looks like this. Oh shoot, I don't want to do it that way. I can draw this circuit now that it looks like this. These are the same circuits. You see how I come to this junction right here and it splits into 3 branches? That's what I do here. I come to this junction and I split into 3 branches. In one of the branches I have 2 capacitors. In the middle branch I have 1 capacitor, and then in the bottom branch I have 2 capacitors. Some students get confused. A lot of students get confused actually. They would say that this is a parallel branch, but recognize that it is not, or rather that, they would say that those 2 capacitors are in parallel with one another because they see that little bend in the wire, and it sort of looks like they're in parallel, but there is no junction between them. Since there's no junction, those 2 capacitors are in parallel. So now that I have it drawn out like this, each of these has 4 microfarads. So to find the equivalent, let's see, these 2 4 microfarads, that's 2. This is 2. So it's 2 plus 2 plus 4. So the equivalent is 8 microfarads. But the hard part about doing it is redrawing the circuit in that way, and students often stumble over that. Well, one, that there's no battery attached to it, and I'm asking for the equivalent capacitance between those 2 points, and then that it's just sort of drawn funky. When you see circuit diagrams, if you've ever gotten like an appliance and it comes with a circuit diagram, open it up sometime because they try to get it all on a single page, and in order to do so, since there's a lot of different electrical components, they have to draw it differently than we usually draw it like this. This just takes up a lot of space. Okay? How are you feeling about these circuits? You're coming with them? I could give you the quiz right now. You do just fine. What if I just gave you like a little preview quiz? And if you make a 10 on it, then we'll just be done. We should do that in the help session sometimes. Let me turn the camera off, and then I'll give you those questions. Yeah, that's a great idea. Man, you're amazing. Okay. Can we try this one? What is the potential across the top left 4 microfarad capacitor? So I want to know what is the potential across this one right here. Well, I'm going to redraw it. I'm going to start with these 2, a 4 and 4 in series. That's 2. So let's just redraw it. That's 2, 2, 4. I have 12 volts down here. I'm doing the capacitance in red, just so I'm getting lazy. I don't want to write the units. Now I'm going to do the 2 and 2. Replace that with a 4 microfarad capacitor, because 2 plus 2 equals 4. So now I have 4, 4, and 12. Because those are identical capacitors, I know that I get 6 volts and 6 volts. That means that this is 6 volts right here. Oh, and that also means that I get 6 volts here and here. The reason I get 6 volts there and there is because this is the equivalent of these two in parallel. And capacitors in parallel have the same voltage. And they have the same voltage as their equivalent capacitance. So they don't split the voltage, they share the voltage. They share the same voltage. So I have 6 and 6 there. And then I'm looking for the voltage across this one. What is it, do you know? It's 3, right. Because I have 6 volts that is split across these two capacitors. That means I get 3 volts and 3 volts across those two capacitors. Okay? Alright. If you see any stuff about voltages of batteries, that's not on your exam. This problem number 4 right here, that was that very last thing. Remember I said, oh, that's just using an equation. It'd be something similar to this. Let's just try it out. So here, you know, like you've done before, you want to write out what you know. So the capacitance is 4 microfarads. I get 30 joules of energy. The energy is equal to 1/2 CV squared. And so I get 30 equals 1/2 of 4 microfarads, or 4 times 10 to the minus 6 times V squared. 215. Looks like C? A? No, it can't be A. Were you doing it in your head?
I did it a couple days ago.
I'm pretty sure the answer is C. Let's double check. No? Is that right? I don't think that's right. Oh, it's the square root. Okay, yeah. Yeah, it's not it. I didn't do the square root. You say it's A? Yeah, so that answer is A. Solve it for V and the answer is A. Okay? Something like that. Something to be careful of. Make sure that you're aware of your units. Anytime you're calculating an energy where you're mixing SI units, always convert to SI. You're never going to go wrong with SI. Sometimes you might have to convert back to the units that you started in, but you're never going to go wrong in SI. And just remember that mu is 10 to the minus 6 and nano is 10 to the minus 9. Those are really the only ones that you encounter. In fact, I think really it's only mu that you encounter in this exam. If you look at the various quizzes, you only see micro. That's a pretty common unit for capacitance, is in microfarads. Lena. Oh boy, okay. So that's, yeah, there are a few exam 1 problems, so sometimes we get to that. Okay. This one? Yeah, so the capacitance of a parallel plate capacitor can be changed by what? Well, I'm going to write that equation. C equals kappa epsilon naught A over D. We'll look at that equation sheet in just a second. So the way that I can increase the capacitance, I can increase the area, just make the plates bigger, they can hold more charge. I can decrease the distance, or I can put, you know, a dielectric in there. I can decrease the plate separation, and that's it. I know what you're thinking, but, you're thinking, but isn't Q is equal to CV? So if I increase the charge, doesn't that increase the capacitance? Or if I increase the voltage, doesn't that increase the capacitance? And the answer is no. That your capacitor, the capacity of your capacitor to store charge is only dependent upon its dimensions. Now, if you put more energy into it, you can get more charge on it, but the capacity of it to store charge, the maximum capacity, is only dependent upon its dimensions. Okay, so by changing Q or V, you're not changing C. Right? While Q is proportional to V, and vice versa, C is not dependent upon Q. Q is dependent upon C, right? So the amount of charge that you store is dependent upon the capacitance, but the opposite is not true. That's a good question. You understand what I'm saying? The capacitance does not change with Q or V. Even though V or Q do change with the capacitance, the reverse is not true. Like a bowl, right? You can hold a certain amount of candy, and you can pour that in there, but if you pour more or less candy, it doesn't change the shape of the bowl. Okay? Well,
The specific one was just a scenario. So when you're using the capacitance equation, like the C equals A over B, if you have the same area as the two capacitors, you only use it once, right?
yes, so let me just repeat what she said. That's a good point. I've seen students make that. Well, here's one, like number 13. So you'll probably have a question like this where you just have to calculate the capacitance of a capacitor given its dimensions. Let's look at that equation sheet, by the way. So, this is one I want. I'll probably just give you, the constants. And notice that epsilon naught is right here. That's the epsilon from the C equals epsilon naught A over D. And then the equation is right here. Although there's an additional equation right here. And the only difference there is that it includes the dielectric. Because in the chapter, we introduce capacitance, and then later we introduce the dielectric. So that's why it's on there twice. Notice, too, that the various forms of the energy equation are right here. Here's our equivalent capacitance. Though recognize that the capacitors in series, the way that we've been writing it is this way. But that's the same. That's the same way of writing it. Yeah, that's it. Okay? So let's go back to that question. It's a good one. C is equal to kappa epsilon naught A over D. Kappa is the dielectric constant. That's 1.8. Epsilon naught is 8.85 times 10 to the minus 12. A is 0.3. Even though there are two plates, this is what you asked, even though there are two plates, your area is what's given. In fact, I'm never going to give you never have to do anything with the number. You just use that number, okay?
But you have two different areas.
You don't have two different areas. Like parallel plate capacitors are designed to have the same size plates. 0.3 square meters divided by the distance, which is 1 times 10 to the minus 6. And then that is whatever it is. I don't know what that is. What's the answer? B. So it's 4.8 you would get times 10 to the minus 6 farads. And then this times 10 to the minus 6 just means micro. Okay? Right. Don't square it. Don't be thrown off. Somebody was with me earlier and they thought, oh, don't I need to square it? No, because I'm not giving you the dimensions. I'm giving you the area. These are just the units that I put there. Okay? I don't know if I ever give you the dimensions, but if I do, I don't remember ever seeing a question like that I've given, where instead of giving you the area, I give you the dimensions. But if that was the case, you would need to calculate the area. I'm pretty sure I haven't done that, though. All right, y'all have other specific questions? I think that's sort of the extent of the quiz. Specific questions? All right, I'll pause this and I'll tell you all the answers.